from yesterday, and then you really will have the rest of the period to work on homework, in case you have any questions on it. And then basically tomorrow we'll be doing expanding area into a type of volume. And then basically your quiz is on Friday of this week, only covering area, and then the volumes by cross sections we'll do on Wednesday. Thursday will be another work day for you. So again, when we're looking at finding the area between two curves, there's like several things you have to consider. Big idea though, if you're doing it in terms of dx, it's the integral of the top function minus the bottom function. If you're doing it in terms of dy, it's going to be the right function minus the left function. This is a very visual kind of topic, like you need to be able to see the region so you know which one is like the top one, which one is the bottom one, or which one is right, which one is left. Even beyond that, how to determine whether you want to do it in terms of dx or dy. These would be some graphs I would expect you to know how to do on your own without the calculator. Let's talk about the easy ones first. X equals 0, that is just the y-axis. Try a different marker. One second, I need a battery. And so x equals 0, see if the battery works. There we go. X equals 0, we know is just the y-axis. Cool, nothing's working today. 1 second, guys, just bear with me. Let's try this again. Nothing wants to work here. Cool. Sorry guys, I'm trying to figure out why my board decided to stop working. All right, guys, this is what I'm going to do. We will finish these notes. But right now, while I troubleshoot technical difficulties, what I want you working on right now, don't leave the meeting here at home because I'm hoping I can get this board working eventually. Go ahead and just start working on homework 1. And yeah, we'll leave that. Start working on homework 1. Did want to briefly talk about test corrections, but I'll do that towards the end of class. Work on homework 1 while I play around with my computer. If you're at home, please don't leave the meeting. You might see me leave the meeting as I restart my computer, but hopefully I can be back in business once I do all that. So yeah, work on homework 1 for a little bit till I decide to start class again.
Mr. Brown, you're muted.
Cool, and I was on mute that whole time, wasn't I?
Yes.
Great day today. Okay. How much of that do y'all want me to go back and explain? I'm fine going through all of it.
All of it.
I'll do all of it.
Yeah, I didn't even know you did anything until I
Yeah,
got back.
no big deal. That's my fault. Rewinding. We'll get through these notes eventually. So we do need to know how to graph it. X equals 0, I kind of did the easier one first. X equals 0 we know is just the y-axis, so I kind of put that in the graph in red. The other one I graphed was y is equal to e to the 2x. That is an exponential function, so we should have a basic idea of what that looks like. Again, you don't have to have a perfect graph, but you do want to have some sort of sketch, so you can kind of make the determination of, is it going to be dx, dy, and kind of like what's the top, bottom function, or the right and the left one. E to the 2x is an exponential one. Plugging in 0 for x, I didn't know that it would have a y-intercept at 0, 1. And then that last function, y is equal to e, I think some people look at that one a little bit weird, but again, e is just a number. It's slightly larger than 2. We know that y equals a number is a horizontal line, so I know that's going to be a horizontal line somewhere above 2. Again, this is just a sketch, definitely not accurate or drawn to scale, but we can see what I kind of shaded in black would be the region that we're trying to find. This one you could technically do in terms of dx or in terms of dy, because the top and the bottom functions stay consistent, also the right and the left functions stay consistent. Since this one is already in terms of x, I'm going to go ahead and do it as a dx problem in terms of x. This region is starting at 0. We can kind of easily see that clearly. We do need to figure out where this region is ending at, and that's going to be ending at the intersection point. How in math do we find the intersection points? Well, we set two graphs equal to each other. So I'm basically finding when e to the 2x is equal to e. Two different ways you can solve that one. You can take the natural log of both sides, or I think what's easier, if I have e to the 2x, which is equal to e to the first, then we know that both of those exponents have to be equal to each other. So 2x would be equal to 1, so x would be equal to 1/2. So the integral that I'm setting up would be from 0 to 1/2 of, again, top function minus the bottom function, all in terms of dx. This problem did ask you to find the area, so we do want to evaluate this one. So evaluating e, again, e is just a number, so what's going to be the antiderivative of e? E is going to act like a coefficient, so that's just going to be ex, minus that second term, e to the 2x, you would want to make sure you do u substitution for. U would be 2x, u prime would be 2, coefficient of 1/2, e to the u is just e to the u. We're evaluating this from 0 to 1/2, so I can go ahead and plug in the top function minus the bottom function. It actually looks really ugly when you go to plug this in, but then it actually simplifies fairly nicely. So I have plugging in 1/2 for x, e times 1/2 minus 1/2 of e. 2 times 1/2 is just 1. There's where I plugged in the top, minus plugging in the bottom. That's going to be 0, so I have e times 0 minus 1/2 e to the 2 times 0. Could definitely leave your answer like that, but we do see lots of things cancel out. 1/2 of e minus another half of e goes to 0. E times 0 is 0. Distributing the negative, e to the 0th power is 1, so the answer to this would just be 1/2. I do like that answer. Again, I know I'm kind of like the math teacher and the dork, but it's kind of like we have this area that definitely has like a curved side to it, created by this exponential function. Definitely not a regular geometric shape, but it has an area that's a nice looking rational number. Questions on that one?
Mr. Brown,
Yes.
the area that is, wouldn't that be the area of y is equal to the 2x that's closest to the x-axis?
No, because you have to look at the integrand that we did. We did e minus e to the 2x. So that is basically representing like if you think about like the height of a rectangle, so we're literally still finding like, there's the top y, there's the bottom y. So we're still finding, yes, that what I have shaded in black region. If I was just finding what was underneath the exponential function, you would have just integrated e to the 2x instead. Which I think is what you were asking.
No, I'm just confused because y is equal to the x. If you integrated that, you would get like a rectangle, but then you're subtracting out e to the 2x, which is the black region for me.
Mhm. Correct, so that does make sense. So if you think about it, so integrating e would be a rectangle, so it's basically, I'll shade it in yellow. That's the integral of e minus the integral of e to the 2x, so you're subtracting this from it. What's left over? This region up top.
No, I was looking at y is equal to the 2x wrong. That's why.
Okay, we good now?
Thank you.
You're welcome. Go ahead and try for me, guys, this one. You're actually gonna do this one twice. So if you finish this one before I go over it, you can go ahead and do the next slide. But basically, I give you two regions. Again, I would expect you to know how to graph those without a calculator. We have to translate a stretched out radical function and then just a line. I first want you to just write an integral for it to be in terms of x. The second way we'll do this problem, just to kind of remind ourselves that we can always just do it both ways. Of course, sometimes there's going to be a way that's much easier than the other way. I also want you to do that same region and doing it in terms of y. But the first order of business is you do want to kind of figure out what this region looks like. Again, it doesn't have to be a perfect graph, but it should be enough so you can kind of visualize what that region looks like. So where we have like a radical function, a line, and basically the y-axis as well. So first step, again, once you kind of try it fully on your own first, draw the region. If you need to find any intersection points, do that, and then set up a definite integral, but don't worry about evaluating it. If you finish this one before I go over it, then go again and do it in terms of y instead of in terms of x. I'm going to give you a few moments to try that one on your own first. And this one, honestly, I think the trickiest part is maybe just doing the algebra to find the intersection points, not really the calculus. So there's my work starting off that one. I haven't quite finished it, but I do want to walk you through it. So again, you can notice my sketch, not perfect by any means, but it does give me an idea of what this region looks like. A radical function we know just has that classic square root shape. It's going to be located at the origin. I kind of drew that radical shape. The line y is equal to 1/2 of x plus 4. That will just be a line that has a y-intercept at 4. Slope of 1/2, so I knew it just needed to be an increasing line. I also was bounding this region the y-axis, so by like drawing that line, I know there's going to be some sort of intersection point that I would need to find. And then I kind of shaded in that light blue, that region that I am finding the area of. How do we find those intersection points? We find those intersection points by saying the two graphs equal to each other. Different routes you can take in solving that to find the intersection points. For me personally, I don't like dealing with fractions when I solve the equation. So I multiplied everything by 2 first, and that gave me 6 on the square root of x, which is just equal to x plus 8. And then next, if I'm solving that equation, I just want to get rid of that radical sign. How do I do that? I can square both sides. By squaring both sides, making sure I FOIL the x plus 8, I see I now have a quadratic. How do I solve quadratics? Get it equal to 0, factor, and then solve. Sometimes when you square both sides in math, you do get extraneous solutions. In this case, we don't. We do get 2 places of intersection points. One of them is located at the x value of 4. There's like another one later, so my graph is definitely not drawn to scale, but it intersects again the graph just from the curve over at 16. But what's the one that is bounding a region? The one that starts at 4. If you want to find that intersection point, again, if I am just doing this in terms of x, I really just need the x coordinate. But I could plug 4 into either the equation, like 3 times the square root of 4, 3 times 2. I know that that intersection point is 4, 6. Then it told me just to write, but not to evaluate the integral. We're doing it in terms of dx. So I first want to figure out how many integrals I'll need to use if I'm doing it in terms of dx. Well, looking at this region, what is the top function stays the top function, and then what's the bottom function is always the bottom function. This region is starting at the x value of 0. It's ending at the x value of 4. And then we want to do top minus the bottom. So I have the top function minus the bottom function, and then make sure I put a dx at the end. Didn't ask me to evaluate it, but that integral would give you the exact area of that region. Questions on that setup? All right, go ahead and do that problem again. So it's the exact same problem, same region, so you don't really even need to regraph it. But write that area now instead of in terms of y versus in terms of x. Remember, when you're doing it in terms of y, everything has to be in terms of y, the numbers and the functions. And then also just make sure you consider how many integrals you need to use. I am going to cheat and just copy over this graph that I just did.
Mr. Brown.
And then do it. Yes.
So what if you used x equals 16? Would that not work?
If you did x is equal to 16, it would not represent the region being described.
Mm-hmm.
And a better way, like if I draw, let me paste that. If I had drawn a better graph, what this region really looks like, if I had been a little bit more careful, is we have, like this is a stretched out square root function. And then we have like this line. So there's technically 2 regions it could have been asking for. This one, it was specifically asking for the one bounded by the y-axis. Like that's ultimately what we found for this problem. There's a separate region that starts at 4 and ends at 16. That's like a little crescent type shape between the curve and the line. But you wouldn't want to include it in your integral, because again, that would be a separate region, and it also would have like a separate top function and a separate bottom function. This one was just talking about the one that was bounded closest to the y-axis. Did that answer your question?
Yeah, it did.
Okay. And I could, just to kind of springboard off of that, if I just changed this question and said maybe like, let R be the region enclosed by y equals 3x and y equals x over 2 plus 4, then I would have only been talking about the region starting at 4 and ending at 16. Not the one bounded with the y-axis as well. So if I'm doing this in terms of y, first step is this: you want to convert your graphs that you have to be in terms of y. So if I have y is equal to 3 in the square root of x, can divide by 3 first. I'm going to like squaring first. So I get x squared is equal to y squared over 9. For that line, again, different ways you can isolate the x. I don't like fractions when I'm solving, so I'm going to multiply by 2 first, and then solve for the x. So those are my two graphs when I think about them in terms of y versus in terms of x. And then if I am doing an integral in terms of y to find the area, we know we're going to do the right one minus the left one. But when I first look at this region, what's on the right is the curve, what's on the left is the y-axis. As I continue up in that region, what's on the right is still that curve, but what's on the left turns into that line. So I can see that this region has a dividing point where we are going to have to use two separate integrals because the left and the right functions are not consistent. The answer you should get for this one, so that first region, again, we're doing it in terms of dy, starts at the y value of 0, ends at the y value of 4. The right function is the curve, which was the y squared over 9. The left function was the y-axis, which we know is basically like x is equal to 0. dy could have definitely left off that 0 there. Added to that, the second region starts at 4, ends at the y value of 6. The right function is still y squared over 9. The left function now is that line. That line in terms of y was 2y minus 8. Thankfully, it didn't ask us to evaluate it, but just set it up. Yes, Anna?
Yes, 6 from like the y value.
The 6, so if I knew the intersection point was 4, I just plugged 4 into one of those functions to find the y that went with it. Any other questions on that problem?
Where'd you get the 0 from?
The 0 came from because that is the left function of that first region. So like when I say the y-axis, what's the equation of the y-axis? It's x is equal to 0. So that's where the 0 was coming from. And again, if you just left off the minus 0, it would still be correct because minus 0 is just, minus 0. Any other questions on that one? All right, so class got started late, but you still have a good 27 minutes to kind of get work done. What I want you working on is basically homework 1. Tomorrow we are going to start volumes by cross sections, and I'll assign homework 2. I will say homework 1 is by far the longest homework we have in this unit, but also all the other homeworks we have will basically build on you being able and being very comfortable with that first homework. You really can't do volume until you're comfortable with the area. So that's kind of your first priority of what I want you to basically be working on. The other thing, if you were virtual, then of course you could probably already see your test because I did go ahead and just leave it in your OneNote after I graded it. If you're here in person, then I'm about to give you your test back. Recovery, again, is slightly different from first semester. The cutoff is now 79 instead of 89. I am still doing, like, the corrections will add 5 points, again, capping it at 79. If you need any more points than that, you will need to do the recovery test. I know the county put the deadlines of, like, the recovery test has to be done within, like, 5 days or before the next summative. But in BC Calculus, where we literally have almost a summative every week, like, that's just not feasible. So I'm going to put the deadline for recovery or corrections that just needs to be done before your next unit test, which for this unit will be on the 17th. But again, most people did very well in the test, so none of that actually applies to you. So y'all can go ahead and continue working on homework 1. Again, it will really help you tomorrow if you get most of homework 1 done now.